YouTube users consume over 1 billion hours of videos daily. In 2023, credit card transactions totaled 53.8 billion for an average of 147.5 million per day in US alone. Generative AI consumes trillions of parameters and petabytes of datasets. We live in an era where terabytes of data are transferred every second. But if we zoom out and peel back the layers all of it, the entire digital world is built on just two things: 0 and 1. How can we use something that simple to build something that complex? Hello and welcome back. Building on our previous discussions about numerical systems and data types, we'll talk about how memory works at the binary level, covering everything from data type sizes and type modifiers to fascinating topics like Endianness and how it affects data storage and operations. Let's get started. The most fundamental building block of memory is bit, a binary digit that can have one of two states, 0 or 1. It's the smallest unit of data in computing, and everything – numbers, characters, images, and even code is ultimately represented using combinations of bits. However, it's not the smallest addressable unit of memory on most systems. A byte, a group of bits, on the other hand, is. But wait a minute, if bit is the smallest unit of data, why don't we operate bits directly? Why is byte the smallest addressable unit of memory, but not the bit? To address the memory means to assign a unique identifier, address, to a unit of storage, so that CPU can access it. Addressing memory at the level of individual bits would be inefficient, because CPUs and memory controllers would need complex circuits to locate and manipulate individual bits, significantly increasing cost and complexity. Operating at such a fine granularity would slow down memory access, as multiple operations would be needed to handle small data chunks. So, bits are too small to be addressed efficiently, whereas byte is a compromise between hardware efficiency and usability. The term byte was coined by Werner Buchholz in June 1956 during the early design phase for the IBM Stretch computer, which had addressing to the bit and variable field length instructions with a byte size encoded in the instruction. It is a deliberate respelling of byte to avoid accidental mutation to bit. The size of the byte has historically been hardware dependent, and no definitive standards existed that mandated the size. Sizes from 1 to 48 bits have been used. The 6-bit character code was an often used implementation in early encoding systems, and computers using 6-bit and 9-bit bytes were common in the 1960s. This system often had memory words of 12, 18, 24, 30, 36, 48 or 60 bits, corresponding to 2, 3, 4, 5, 6, 8 or 10 6-bit bytes, and persisted in legacy systems into the 21st century. In this era, bit groupings in the instruction stream were often referred as syllables or slab, before the term byte became common. Early computers used a variety of 4-bit binary-coded decimal representations and the 6-bit codes for printable graphics patterns common in the US Army and Navy. These representations included alphanumeric characters and special graphical symbols. These sets were expanded in 1963 to 7 bits of coding, called the American Standard Code for Information Interexchange, or ASCII, as the Federal Information Processing Standard, which replaced the incompatible teleprinter codes in use by different branches of the US government and universities during the 1960s. ASCII included the distinction of upper and lowercase alphabets and set of control characters to facilitate the transmission of written language as well as printing device functions, such as page advance and line feed, and the physical or logical control of data flow over the transmission media. During the early 1960s, while also active in ASCII standardization, IBM simultaneously introduced in its product line of System 360 the 8-bit extended binary code decimal interexchange code, an expansion of their 6-bit binary coded decimal representations used in earlier card punches. The prominence of the System 360 led to the ubiquitous adoption of the 8-bit storage size. In the early 1960s, AT&T introduced digital telephony on long-distance trunk lines. This used the 8-bit mu-long encoding. This large investment promised to reduce transmission costs for 8-bit data. The development of 8-bit microprocessors in the 1970s popularized this storage size. Microprocessors such as the Intel AT80, the direct predecessor of the AT86, could also perform a small number of operations on the 4-bit pairs in a byte, such as the decimal add adjust instruction. A 4-bit quantity is often called a nibble, also nibble, which is conventionally represented by a single hexadecimal digit. Today, a byte is almost universally 8 bits. It is large enough to represent common data units like characters, in ASCII for instance, or small integers. Most modern CPUs are designed to work with bytes or multiples of bytes, for example 32 or 64-bit architectures. Byte-line memory access is faster and more straightforward. Memory hardware like DRAM and SRAM is organized in blocks or words that align naturally with byte boundaries. The byte is now the universal standard for memory addressing. Now, here's an important question. How many different values can we store with a given number of bits? Let's break this down logically. If you have one bit, it can represent two states, 0 or 1. Adding a second bit doubles the combinations, giving us 4 possibilities, 0, 0, 0, 1, 1, 0 and 1, 1. A third bit doubles this again, to 8 combinations, and so on. Overall, the number of unique values that can be stored in n bits is calculated as 2 in the power of n, because each additional bit doubles the number of possible states. Let's look at a few examples. 3 bits can store 2 in the power of 3 or 8 values, ranging from 000 to 111. 8 bits, or 1 byte, can store 2 in the power of 8 or 256 values, ranging from 8 zeros to 8 ones. Data types like int, char and double occupy a specific amount of memory, which determines how large or small the values they can represent are. For example, in C++, an int is guaranteed to have a width of at least 16 bits. However, on 32 or 64-bit systems, it's almost exclusively guaranteed to have width of at least 32 bits, or 4 bytes, which allows it to represent 2 in the power of 32 unique values. In C++, type modifiers like short, long, signed and unsigned are used to adjust the behavior or size of primitive data types. Short specifies that the target type will have width of at least 16 bit, long at least 32 bits, long at least 64 bits. These are not standalone types, but modifiers that adjust the behavior or size of another type. If you don't specify a type explicitly, int is assumed. For example, short x equivalent to short int x, long y equivalent to long int y, and so on. Signed and unsigned are used to adjust the range a data type can represent by shifting it from both positive and negative values to only positive, and vice versa. We will cover that in more detail in the following video. Not all types can have modifiers. Here's the breakdown. Int can be modified with short, long, signed and unsigned. Char can be modified with signed or unsigned. Double can only be modified with long. Types like float or bool cannot have modifiers. While talking about the positional notation in scope of numerical systems, we said that the rightmost digit is the least significant. For example, in the number 345, the rightmost digit 5 is the least significant digit. It represents 5 multiplied by 10 in the power of 0, while number 3, in this case, is the most significant, because it represents 3 multiplied by 10 in the power of 2. While this is true for the decimal system, we simplified it when we were talking about the same scenario for the binary system. The rightmost digit is not always the least significant for binary. This is called Endianness. Endianness determines the order in which bytes are stored in memory. For Big-Endian, the most significant byte is stored first, at the lowest address. while for little-endian, the least significant byte is stored first. Let's take a 32-bit integer as an example. While the data remains the same, the order of the bytes is flipped. This difference is crucial when interpreting binary data from external systems or files. Endianness exists because different processor architectures adopted different conventions. For example, Big-Endian is more intuitive for humans as it stores data left to right, like in decimal numbers. Little-endian is used in most modern architectures because it simplifies certain arithmetic operations. Little-endian simplifies multi-byte arithmetic because it matches the way arithmetic is processed in the arithmetic logic unit. For example, when adding two numbers, the CPU starts with the least significant byte and works its way up. In little-endian, the least significant byte is stored first, so the CPU can process each byte in memory sequentially without needing to rearrange the data. In contrast, Big-Endian requires extra step to jump to the most significant byte first, making arithmetic slightly less efficient. Finally, let's look at a simple C++ program that demonstrates type sizes and modifiers. Curious about endianness of your local system? We've got a little something for you. Follow the link in the description to find a code snippet that allows you to find out just that. Today, we've explored the fascinating details of how integral data is represented in memory, looked at the data type size modifiers, and explored endianness. We've seen how the size of a type affects its range and learned how endianness affects arithmetic efficiency. Thanks for watching and happy coding!